Hello and welcome. Today, we're going to explore a fundamental concept in fluid mechanics, shear stress. Shear stress is essentially the force per unit area that a fluid exerts tangentially or sideways on a surface, or that layers of fluid exert on each other as they slide past one another. Imagine spreading honey on a piece of toast. The resistance you feel as you spread it is directly related to the shear stress within the honey. To understand shear stress better, let's consider a classic setup. We have two large, flat, parallel plates. The bottom plate is fixed and stationary. Between these two plates, there's a layer of fluid, like oil or water. The perpendicular distance between the plates is h. Now, what happens if we apply a tangential force, let's call it F, to the top plate, causing it to move at a constant velocity? U, because of the fluid's viscosity, the fluid layer in direct contact with the top plate will stick to it and move at the same velocity U. This is called the no-slip condition. Similarly, the fluid layer in contact with the stationary bottom plate will remain stationary. The fluid layers in between will slide past each other, creating a velocity gradient. The fluid essentially deforms or shears. This difference in velocity between adjacent fluid layers creates what we call a velocity profile. For many common fluids, under these conditions, the velocity increases linearly from zero at the bottom plate to U at the top plate. The rate at which this velocity changes with respect to the distance, y, perpendicular from the stationary plate, is called the velocity gradient. The shear stress, denoted by the Greek letter tau, is defined as the applied tangential force, F divided by the area A of the plate in contact with the fluid, SO, taf equals F over A. This gives us a measure of the internal resistive force per unit area within the fluid. For many common fluids, called Newtonian fluids, there's a direct relationship between shear stress and this velocity gradient. This relationship is known as Newton's law of viscosity. It states that the shear stress is directly proportional to the rate of shear strain, which for our setup is the velocity gradient, often written as dou/dysprosium. Here, dou represents a small change in velocity between two adjacent fluid layers, and dy is the small perpendicular distance between these layers. The constant of proportionality is called the dynamic viscosity of the fluid, denoted by mu. So the formula becomes tau equals mu times dou/dy. Viscosity, mu, is a measure of a fluid's resistance to flow or shear deformation. Think of honey. It has a high viscosity. It resists flowing easily, so a larger force F is needed to move the top plate at velocity U. This means it generates a higher shear stress for the same velocity gradient dou/dysprosium. Water, on the other hand, has a low viscosity. It flows much more easily, requiring less force and resulting in lower shear stress for the same velocity gradient. Viscosity depends on the fluid itself and often on its temperature. The term dou/dy is the velocity gradient, also known as the rate of shear strain. It tells us how rapidly the fluid velocity, U, changes as we move a small distance dy perpendicular to the direction of flow. In our simple case, with a linear velocity profile, if the top plate moves at velocity U and the perpendicular distance between plates is h, then the velocity gradient dou/dy simplifies to U divided by h. So for this specific scenario, the shear stress tau equals mu times U over h. So to summarize, shear stress in a fluid arises from the cohesive forces between fluid molecules and the momentum exchange as layers slide past each other. It's defined as force per area, F/A, and for Newtonian fluids is given by Newton's law of viscosity, tau equals mu times dou/dysprosium. Understanding shear stress is crucial in many engineering applications, such as designing pipelines, analyzing blood flow, determining the drag on vehicles and aircraft, and in lubrication systems. Thank you for watching.